so we have to proceed with the next presentation that will be given by Danila Prikazchikov from United Kingdom, Kiel University, and the name of the presentation is Rayleigh waves on a coated elastic half space.
Okay, thank you very much. So it's a pleasure to participate for the second time in the APM. And this is a joint result together with Professor Julius Kaplanov from Kiel and also our former PhD student Leila Sultanova, who is now at Warwick on a postdoctoral fellowship. And here is the outline of my talk. So first we will be talking about surface waves on a coated half space, but in case of a rather specific boundary condition. So it will not be a free surface, but it will be clamped surface. As usually, if the half space was homogeneous, then there will be no possibility for Rayleigh waves to propagate. But because we will have this inhomogeneity due to a coating, it seems to be possible. So we will derive the dispersion relation, study it a little bit from a numerical perspective, depending on the different parameters of the coating and the half space. Then we will try to tackle the problem from asymptotic perspective. So we will derive effective boundary conditions, which will model the effect of this small thin coating. And then, as it will turn out, the Rayleigh wave is quite relevant there, even with the fact that we have a fixed surface of the coating. We will apply the asymptotic formulation for the Rayleigh wave and establish a correction to the Rayleigh wave speed. And then at the end, we will compare the results that we've got for this fixed surface boundary condition to the known results for the free surface in case of a coated half space. So usually, just as I was saying, if we have a homogeneous half space and we have a clamped surface, no displacements here, there'll be no Rayleigh waves. That's very clear and well known. However, if you take the inhomogeneous half space and still clamp the surface, it seems possible. Some localized solutions are possible. And there was a recent paper that has proven this possibility by Kirill Chernyshenko and his co-worker Shane Cooper. So where we just wanted to illustrate this, and for simplicity we've taken just one layer. So we are considering a half space, and there is a clamped surface here, but this layer we can think of being a sort of a soft layer. Because if we think about it, if you have a soft layer, say some sort of a foam, attached to a hard layer, a hard half space, say this would be metal, then even though this surface is clamped, but because of this layer being soft, it can actually vibrate, and then this interface is not really clamped. It is not free, but still there is a possibility for waves to propagate. So this is our sort of physical insight before doing any analysis. So we can hope for some localized waves there. So if we write the equations of motion, first try to derive the exact dispersion relation, we can write the usual plane strain equations of motion. Here, plus and minus for quantities will be associated with the half space and the layer, respectively. And we write the simple constitutive relations for isotropic linearly elastic solids. The difference is certainly the boundary condition. So at x3 equals minus h over here, our surface is clamped. So we have no displacement. And we assume continuity in displacements and stresses along the interface. This is our formulation. So if we decompose our problem into linear elastic potentials, the usual format, then we are rewriting the equations of motion as wave equations for the potentials. Here C1 and C2 will be the wave speeds. Here they are, and the Laplacians. So we seek for our solutions in a very conventional form of traveling harmonic waves, and within the layer we are having this trigonometric dependence, and for the half space we have exponential decay, right? So if we substitute all these into our boundary and continuity conditions, we will have a 6x6 system, and the determinant of this equal to 0. That will be the condition for usual, well, having non-trivial solutions. So this will be our dispersion relation, and we can plot it. So the natural parameter that appears there is a ratio of shear moduli, and we also perform non-dimensionalization. So we relate the phase speed c to the shear wave speed of the half space, and also we introduce the dimensionless frequency and dimensionless wave number. We've picked up some material parameters just to perform the computations. So we're fixing them, but we are changing the ratio of shear moduli, and we can see that certainly a lot depends on it. Because, of course, if mu was 1, then it could be the situation, well, if all the other parameters would also coincide, it would be the situation of a homogeneous half space. And certainly in this case, there would be no solutions at all. However, we can see that with the growth, when this parameter mu, the contrast is growing, so we are moving from, say, 0.5 to 0.1, so the ratio would be 10, then certainly some solutions do appear. And I will show you later on the situation when we have mu as 1 over 1,000, as far as I remember, and there certainly there is a much clearer picture. But we can clearly see a lot depends on this ratio. Okay, so first of all, before tackling this, we decided to have a look at a simpler problem, which would be Love-type waves. So the antiplane problem will have a very similar situation. We will also put the precluded displacements on the surface of the coating and assume continuity. So in this case, the dispersion relation is much easier, so we can work with that. And this is explicit, but the figure, well, the figure of the dispersion curves is actually quite similar. So we can study this analytically. And first of all, we can certainly observe that these two lines here, the boundary lines, the yellow one and the green one, are very clear. They are associated with the speeds. So they are associated with the shear wave speeds, as we would expect for classical Love waves. So we see that our curves start originating on this yellow line. And we can find these initial points because this is one of the limits. So this is the case where this tangent blows up. And then here are the coordinates of these points. So both omega plus and k. So here it's gradient 1 because it's been dimensionalized to the 2C2 plus. And then we can also find the other limit where, well, the shortwave limit when k is large. So that will be another limit where c tends to C2 minus, the shear wave speed in the coating. And here we have some evidence of that on the figure. It's clear that all the curves will be tending eventually to this line, right? So we have this existence triangle, and this elementary analysis of Love-type waves gives us a hint that the same idea will be valid for surface waves. And we could do similar things. The only difference is that certainly the dispersion relation is not that explicit. So it's a huge 6x6 determinant. So it's really difficult to simplify it. But what we could do, we could certainly substitute this value of c equals to C2 plus. And the same idea is true that the dispersion curves start originating on this yellow line associated with the shear wave speed for the half space. and then they tend eventually tend to their asymptotic values here. You can find this approximation for shortwave region. However, if we want to find these coordinates of the red originating dots, it will be more difficult because we'll probably need to do that numerically. So we would need to substitute this into the dispersion relation and then solve it. But it's the same idea. What else can we see here? We can see that with the growth of contrast, say here the ratio of mu's is 2, here is more than 3, so we have more solutions within the same region, so we would have more branches. And we can also see that the first branch tends closer to 0 for the relatively higher contrast. Okay. So now if we take really high contrast, the thing that I promised you, so we have about 1,000 here, then obviously the first branch will start very closely to 0, but it will still be non-zero. So obviously there is still the same mechanism. The coating is not allowing the wave to propagate from the origin, because there is still some sort of a band gap there, although this band gap is tending to 0 as soon as the contrast in principle tends to infinity. So what we can see, all these branches, they are growing. There are some problems associated with thickness resonances, and these are shown here by the dashed line. So there are thickness shear and one thickness stretch resonance found here in this domain. And also with this red dashed line, we are showing the straight line associated with the Rayleigh wave. So this line has a gradient associated with the Rayleigh wave. So we see that the Rayleigh wave is very much related to the wave we found, I mean the Rayleigh wave in the half space, although certainly in the vicinity of these resonances, it doesn't work. So we could consider this problem for resonances separately and derive the conditions for these frequencies. So that would be just the usual eigenvalue problems for this layer. Right, so there'll be one associated with stretch and another corresponding to shear. So certainly if we have this Rayleigh wave being so close, that will give us motivation to apply the asymptotic model for the Rayleigh waves in future. But as for now, let us concentrate on these resonance frequencies and derive effective boundary conditions for this layer. So suppose that we have this thin coating, so we consider it separately now, with a clamped face and some prescribed displacements on the lower face. And what we aim for is to derive effective boundary conditions that would give us stresses on the interface that would summarize all the effect of this layer, right? So this is a relatively standard approach here. We would use asymptotic integration, a method due to Professor Goldenweiser. So we will have a small parameter here, the lone wave approximation, and we would introduce dimensionless variables and also dimensionless frequency here. The important thing is that we are talking here about high frequency, not a low frequency approximation. So this omega minus would be of order 1. We can, yes, this is another confirmation here. And we are scaling the displacements and stresses. And the main message here is that all these quantities with an asterisk are assumed to be quantities of the same asymptotic order. And so we are talking now about long wave high frequency approximation. And if we will substitute all these quantities into governing equations, then we have a system of PDEs, and then all these quantities with the asterisks will be expanded as asymptotic series, and we could start our procedure. So we will perform sequential integration of these equations. Right, so if we do that, this is what we get at leading order. So the important thing to note here is this omega minus squared here. So that is associated with the fact that we will have trigonometric variation along the thickness, but not a polynomial one. So if we were to focus on the long wave low frequency, then this omega minus would be small and wouldn't come at the leading order. And in this case, the variation, the leading order variation would be polynomial across thickness. So this would be associated with the free-type boundary condition. But since we are dealing with a fixed one, actually we have high frequency, and this omega minus squared appears in this equation. So at leading order, this is the solutions that we have, and these are the leading order stresses. So as predicted, there are certainly, well, sinusoidal variation along the thickness. And we can now formulate the asymptotic boundary conditions, which are effective boundary conditions on this interface, right? So they are non-traditional because they have this cotangent factor. So it means that at these thickness resonant frequencies, they will blow up. But that's life. So now, once we've got effective boundary conditions, we have a half space with these stresses applied at the surface, and we can use our asymptotic model for the hyperbolic elliptic model for surface waves, which is a simplified version of elasticity, but it allows us to describe the contribution of the Rayleigh wave by the and the compromise is that we are neglecting the bulk waves contribution. So we get a hyperbolic equation here, and on the right-hand side, we have a constant times this guy here, which is, so the over bar is a harmonic conjugate, and this is the derivative with respect to, so it could be sort of a Hilbert transform, really. So if we put this, well, start analyzing this equation and want to derive the associated dispersion relation, this is what we will have. So if mu is small, then at leading order, we have just zeta equals to zeta r. So that would be associated with c equals to cr. Yeah, thank you. However, if we want to get a correction, this is what we will have. So this will be the corrected coefficient here, and this is the resulting approximation. So we have this Rayleigh wave speed plus a correction. But the problem with this correction is that gamma potentially might blow up at these resonant frequencies associated with thickness resonance. So here are some numerical plots showing that certainly if we take higher contrast than this model shown by red lines, the approximation works quite well. And if the contrast is not that great, then certainly it's still a little bit far away. And finally, I wanted to compare the results for two types of boundary conditions. So if we have a free surface and fixed surface. So this is a known result from 2010 of a free surface. And as you see, it was a singularly perturbed hyperbolic equation on the surface. So this was a singular perturbation, and this was associated with the long wave low frequency limit. Whereas now when we have fixed surface, it is a different one. It will become a regular perturbation here, and this is associated with a long wave high frequency approximation. And here are the two types of effective boundary conditions. So these were the for the free surface, and you see this is a polynomial variation in terms of psi 3. whereas the new boundary condition that we've just derived, they are trigonometric and they are associated with the fixed surface. That's it. Thank you very much. And here are some conclusions. Thank you very much for your time.
Yeah, thank you very much for this very interesting presentation. Unfortunately, we do not have, so we have to keep to the schedule. Okay. So we don't have any time for questions right now. But after 2 more presentations, we will have 10 minutes coffee break. So if you keep your questions until then, you will have a possibility to ask. Ask them if,
so maybe if I can have just one more final remark, is that the main message is that usually we would feel that if there is a fixed surface, there will be no Rayleigh waves. But this study shows that in principle, it is possible due to inhomogeneity. Thank you.
Yeah, this is very interesting.
We got a question here from Maria Wild.
Maria, you can now ask your question.
Danila, hello. I have one question for you. The question is, your asymptotics for the effective boundary conditions is valid in the small vicinities of thickness frequency. Is it so?
I would say the asymptotics is not valid near the near the thickness.
Not valid. It's very small vicinity.
Yes.
It may be. But what about another ranges of frequencies? It's also interesting to have effective boundary conditions for these cases.
I think that there is a possibility to think about the vicinity of this of the thickness resonances, but it would need to be probably a different asymptotics.
It's possible to construct these asymptotics.
I would think so, yes. I think it is possible, but it will be more difficult.
It's very interesting.
Yeah, okay. We could maybe discuss, yeah, why not? Yes, because of course, the interesting thing about this asymptotic is that this correction to the Rayleigh wave speed is non-regular in effect. Yes, yes. So it will require a special type of asymptotics for this vicinity. Yes, we could discuss.
Oh, why it's so complicated?
It will be more complicated. I agree. Yes, yes, but possible.
Possible. No.
We did not do it yet, so we can discuss. Yes.
Yes. But can I have one more question?
Sure.
Yeah, absolutely. We are good with time now.
I not quite understand. If mu is small, you have Rayleigh wave. If it's not, you don't have. Yes. So it is.
I would say if mu is small, then Rayleigh wave for a number of in the good region, in the good domain, you will have Rayleigh wave approximating. Yes, so it will be close to Rayleigh wave. But if you, because you see, for example, say if you take a half space, say with metal, and put something, I don't know, put some wood on top, it's not, it will be some sort of a Rayleigh wave, but not really. So if you would put, instead of wood, you would put some very soft foam, then certainly your metal half space is almost free. So you will have an almost free Rayleigh wave. It will be in higher, for large frequency domain.
What is not quite Rayleigh wave? We can say its Rayleigh wave was similar to Rayleigh wave. Its speed less than the speed of shear wave. Yes. If it's higher than speed of shear wave, it's not Rayleigh wave. Is it so or not? What is
I don't think there will. You will not have anything. Well, I mean, if you will have higher than this C2, then it will not be localized, I think.
No, it can be leaky waves, but it's not Rayleigh wave.
Yeah. So we are restricting ourselves to these waves which are in between these two C2s. I mean the the shear wave for the half space and the shear wave for the floating layer.
Less than shear waves for the half space, but higher. Yes, it's possible. It's possible. I look in such a problems. It's very interesting. One more question.
Well, if nobody else is there, then yeah, you can continue with your questions. If somebody else wants to ask something, just interrupt.
It's a question, how about the case when we have two half spaces and in between small layer, but soft? It is possible to construct some effective boundary conditions instead of, to simplify the problem, contact conditions between these half spaces through thin soft layer. It's possible.
Yes, I think it's possible. I was thinking a little bit about this type of structure, so that would give you a Stoney type wave. But I haven't done it yet. Yes, so I think it would be possible, a similar thing to be done between two half spaces to have a thin layer. Yeah.
So, but not in the vicinity of the thickness frequencies, but long wave asymptotics are possible or not? Long wave frequency and long waves as is in your paper about free surface.
Yes. Yeah, I think that's possible. Yeah.
Thank you. It's all very interesting. Thank you.
Thank you, Maria.
Okay, any other question to Danila or